everyone and welcome to ML Done. So previously we talked about decision trees and I showed you how you can train a decision tree, and I also talked to you about how you can extract rules out of a trained decision tree. Now there was one question that we didn't answer, and that was how a decision tree decides which attribute to start splitting from. And today we're going to start talking about that concept, but first we need to talk about this idea of entropy. Okay, so let's start. So this is our old data set. So just as a reminder, we had age, height, and salary of different people, and the question was, can we determine whether they're single or in a relationship? And here, as you can see, we've got 5 yeses, meaning that these people are are single, and we've got 4, 5, 6 other people who are not single, meaning that they are in a relationship. And we can see their age, height, and salary. In terms of salary, you can think about that in a month, like $2,000 a month, $2,500 per month. And as you can see, we're trying to predict single, which is the target feature that we're trying to predict, or we want to learn to predict. So the features that we can use for our decision tree are age, height, and salary. Now, as I said, the question is which attribute to choose out of these 3. And there is indeed a quantitative metric for us that would tell us which attribute is worth more in terms of training our classifier, training a better decision tree classifier. And that metric is called the information gain. Now, in order for us to understand information gain, I first need to talk about the building block of information gain, which is called entropy. So let's start with entropy. Right, so entropy is some sort of a measure that would tell us if a set of data is pure or impure, and it will tell us how pure it is. So for example, you can think of our training set that we showed you in the previous slide as the set that we're talking about, and let's call that S. Now entropy will take a look at this set, and in particular it will take a look at the target values, which in our cases are yeses and nos, and it would tell us how impure or how pure, whichever you like, that set is. Now let's look at the math behind it. So this is the mathematical definition of entropy, yes? So we got the entropy of S. So you can think of this S as a, well, subset. Let's call it a subset of data, right? So it can be your training set, and as you go down a tree and you keep splitting and splitting, you kind of make the set shrink into subsets, smaller and smaller, until you get to the leaves, where you would have either instances from class positive or instances of class negative. In our case, either everybody is a yes or everybody is a no in our leaves. So here, what are we saying here? So P plus means, so P stands for proportion, yes? So this is the proportion of positive examples in our subset, in our subset S. Okay? And as you can see, and I'm sure we can guess this by now, P negative is the same story, but it is the prop or proportion of negative examples, again, in our subset S. And we got the multiplication by the logarithm of the same values. So P plus multiplied by log of P plus, again, P minus multiplied by log of P minus. Now notice that in entropy, we're always dealing with the basis of 2. Okay, the logarithm is always has always the base of 2. And that is very important. So, and also, don't forget about these negative signs, okay? So we also have a negative sign. Now, if this doesn't make sense, that totally is understandable. So we're gonna jump into an illustrative example to really understand what this thing is telling us. So remember, entropy is always applied to a subset. Don't forget that. Right, so this is our training set. Let's call it S. And yes, this is the same S that we've been talking about. So we want to measure the entropy of this set, meaning our training set. Now, entropy, remember, it always focuses on the target feature. This is very important. The target feature of your set S, or the subset S, whichever you like, okay? And if you look at here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 examples, right? So we got a total of 11 examples, yes? And we've got, out of them, 5 yeses, meaning that our positive examples, we got 5 positive examples here. And we've got 6 negative examples here, okay? Now, it's more or less 50-50, right? So out of 11 examples, 5 of them are positive, meaning that they're single people, and 6 of them are not single, meaning that they're in a relationship. Now, if I ask you how confused this set is, how uncertain are we about the set, how mixed this thing is, well, intuitively speaking, I think you will agree with me that, okay, this is a pretty mixed up set. So the presence of positive and negative examples are almost equally powerful. Okay, so they're almost equal. And we're a little bit confused here as if, so what makes a positive example positive and what makes a negative example negative? It seems that in our training set, they're equally powerfully present. So that is entropy. So it seems that the entropy, the uncertainty, the confusion in this subset S is high. Now, we're gonna go ahead and compute it numerically. So as I said, this is S, and as a reminder, this P plus, let me change the color, P plus is the proportion of positive examples, right? So we've got 5 positive examples, yes? Cool. And we've got 11 examples in S in total. So P plus would be the proportion of these positive examples, which would be 5 over 11, multiplied by, let's denote that by a little dot, the logarithm of, again, P plus, which is 5 over 11, right? Let's not forget this minus sign here. Again, minus, so P minus, what is that? So we got 6 negative examples here, and in total we've got 11 examples. And then this would be multiplied by the logarithm of, again, P minus, which is 6 over 11. Yes? And so we're going to compute this. Let me just fast forward to where we get the actual result. The entropy of our set S equals 0.994. One thing that you have to know about entropy is that when it comes to a binary classification, meaning that you've got 2 possibilities for your target feature, you always have a maximum entropy of 1, and you would always have a minimum entropy of 0, right? So for the case of binary classification, you can always say that the entropy, let's call it E of S, for the case of binary classification, is always bounded between 0 and 1. And that is the rule. Don't forget that. Why is this the case? I have explained the details about this and mathematically proven for you why this is the case in the blog post that I've posted in the description to this video as well. So you can just refer to my website and see the exact derivation as to why that happens. So, considering that 1 is the maximum, we can conclude that this entropy is quite high. Okay, this is what we actually expected in the first place. We were expecting to get a lot of entropy, a lot of confusion and uncertainty, which is cool. Now, let's see how a decision tree manipulates this entropy. Remember, I'm not telling you how the decision tree chooses attributes on which it would do the splitting. I'm just going to show you as the decision tree is being trained, how will that entropy change? I want you to actually see what is the trend of change in the entropy as the tree grows. You will see an interesting pattern actually. So then again, it's about the same data set, so you can just go back and take a look at that. But as in our last video, we saw that the decision tree chooses salary, and by some mysterious method, it chooses $2,800 per month as the threshold for doing the splitting on this attribute salary. Okay, and we just showed you that in the very beginning, before we even start the splitting, the entropy of our set that has 5 yeses and 6 nos is 0.994, which is a lot of entropy. Now, as we talked the last time, for a part of the data set, this condition holds, and that is what we have on the left side, true, and for a part of that, for a subset of that, this condition doesn't hold. Now, I'm not going to consider the right side of it because I just want to show you how the entropy changes. Okay, so I'm just going to focus on the left side. Now, let's see which part of the data set survives this condition of salary smaller than $2,800 per month. So, this is what happens. So, as you can see, in this new subset, we've got 4 yeses and 1 no. And if you notice, onto the salary bit, over here, the salary attribute, as you can see, all of them are below $2,800 per month. Okay, so that is how we are filtering as we're training our training set. Now, let's compute the entropy at this stage. Remember, it used to be 0.99. Let's see how it changes. Okay, there we go. So, in this new set, if you want to compute the entropy, we've got 5 examples. Okay, and 4 of them are yeses and 1 of them is no. So P plus would be 4 over 5 and P minus would be 1 over 5. And that is how, if we compute the entropy, we realize that the entropy becomes 0.72, which is less than 0.99. Now, let's see what sort of attribute will the decision tree choose at this stage and what sort of threshold for that continuous attribute that the decision tree will choose. So then again, the decision tree is going to choose salary, and well, it happens mysteriously, but we're going to talk about this, okay? So don't worry about that. And it also chooses the value of 1,250. So we are again splitting. Remember, the main reason that we are splitting is because the entropy is still not 0. We will keep splitting and splitting and splitting until we reach the leaves which has absolute 0 entropy, or they're absolutely pure. So having 0 entropy means that the set that we're looking at is absolutely pure. Now let's see what happens. So in terms of true and false for this particular condition, let's see what sort of subsets we're going to get. There we go. If this condition holds, the only entry that will survive is going to be this guy right here, down here, right? This one. Because if you notice our data set over here, the only person that has a salary less than 1,250 is this guy right here, the one in the gray color, and that is why that is the only guy that survived this bit. And if that condition doesn't hold, we've got everybody else who are single that fall on the right side over here, okay? Over here. So let's compute the entropy for each one of these cases. Remember, here on the left we have 0 yes and 1 no, and on the right we have 0 no's and 4 yeses. So in a way you can see that these two sets are absolutely pure, and these are basically the leaves of our decision tree. Now when I say pure, I mean 0 entropy. I mean we are absolutely sure that either they're all yeses or they're all no's. Okay, now let's compute the entropy and see whether we can actually get 0 entropy or whether we can get actual 0 entropy or not. Right, so on the left we got 0 yeses and 1 no's, right? So the p plus proportion of positive examples would be 0 over 1. And we got 1 over 1 for p minus. And if you do the calculation over here, you'd see that, well, log of 1, we know that log of 1 is 0, okay? And 0 over 1 over here is 0. The result of all of this will become 0, and that is when we have 0 entropy. So this confirms what we've been talking about. And on the right side, it's the same story. We've got 4 over 4, which would be the proportion of positive examples. So we've got 4 examples in our set, and all 4 of them are yeses, and none of them are no's. So the p negative would be 0 over 4. Then again, log of 1 is 0, and here the proportion is 0, right? So the result of this calculation is also 0. Now, if you notice, if you see the pattern over here, you can see that it seems the decision tree is trying to reduce the entropy. It's as if as you're going down in the decision tree from the root to the leaves, your entropy is also going down. Okay, so whatever the way the decision tree is choosing the attribute, and whatever the way it's choosing the thresholds to split your set, whatever it is trying to reduce the entropy. It is trying to maximize the certainty. And over here, by the way, we've got log of 0, yes, over here. So 0 over 1 is 0, log of 0. Remember that log of 0 is undefined, okay? So the question is, how did we come up with 0 as for the result of that? Again, in the blog post, I've explained this, and I've got kind of cool visualizations and explained why we can kind of eliminate this whole thing as 0. But I'm not going to digress into that either. That is just a different level of detail. Now that we are a little bit more comfortable with entropy, let's take a look at the behavior of this entropy, right? So we know that the minimum is 0, and we know that the maximum is 1. Here we can see a visual representation of that. On the horizontal axis, you can see the p positive case, right? It's exactly what I've talked to you about. So this is the p positive. And since it's a proportion, it can go from 0 over here all the way to 1, right? A proportion cannot be more than 1. And we've got the entropy. The entropy goes from 0 to 1 over here. So if we actually plot the entropy, meaning that actually consider different values for p plus, and then actually plot the entropy, this would be the shape that you'll get, the one in the red, okay? It obviously has a maximum, and if you take a look at the maximum, you'll see that the maximum happens at 1. And the interesting point is that I want you to take from this is that when the entropy is 1 in a binary, again, this whole thing is about binary classification. In a binary classification, when the entropy is maximized, it means it only happens when the p positive, the proportion of positive examples, is again absolutely, is definitely half of your training set or your subset. Okay, so meaning that if half of your examples are positive, that inevitably tells you that the other half, meaning the p negative, which is 1 minus p positive, because it's a proportion, right, is also 0.5, right? So meaning that the whole training set has been equally divided between positive and negative examples. That is the absolute state of confusion. Okay, they're both equally represented in your set. And that is one that, so that is the case where we can't say which one is more dominant. We can't come up with some sort of a nice rule as to, okay, which one is stronger, which one, we can't make up our mind as what makes a person single or in a relationship. So we want to let the tree grow so that we would reduce this entropy more and more until we get to 0, which is the case with the leaves. Now, according to this diagram, when is entropy 0? That is when the p positive is 0, which implies that p negative is 1, right? Remember that p positive and p negative always, if you sum them up, always sum to 1 because they are proportions, okay? So if p positive is 0.25, p negative is 0.75. So they have to sum up to 1. So if p positive is 0 and p negative becomes 1 naturally, that is when the entropy is 0 because everything you got are negative examples. And the other way around, if p positive is 1 and p negative is 0, then it means all the examples in your subset S are positive. So again, this is a pure set. And this is the state of pure certainty, and that is when you reach to the end of your tree, meaning that you've reached to the leaves of your tree. Now, what about the state of absolute chaos and entropy, which is when the entropy is 1? So that happens in a binary classification. That happens when you've got equal number of positive and negative examples. So if you've got 1,000 examples in your training set, half of them are positive and the other half are negative. That is when you have the entropy of 1. So p positive and p negative are, both of them are 0.5. And that is the state of absolute confusion. Now I'm sure that you can guess when the entropy is neither 0 nor 1. That's right. That is when the proportions are not equal. For example, let's say here, right? This is where we hit 0.3 for p plus, right? So the proportion of the examples in our set that are positive are 0.3. This means that the proportion of examples that are negative are 0.7, okay? But I'm not showing it here, but it is implied. So if I ask you, what is the entropy for the case where p positive is 0.3, meaning that 30% of your data are positive, all you have to do, I mean visually speaking, is to just follow this plot over here. So this would hit, let's say, somewhere around here, and then the corresponding entropy value would be somewhere around here, something between 0.8 and 0.9, okay? So as you can see, it is neither 0 nor 1, and it falls in this range between 0 and 1. Cool. So remember, everything up to here has been the case for a binary classification problem. Now there are cases where you got more than 2 types of labels in your target feature. Okay? In those cases, the entropy changes just a little bit. Okay? And let's just take a look at how it changes. There it is. This is the entropy that we've been talking about over here, right? Now, this might look a little bit intimidating, but if you notice, this is actually more or less the same thing that we've been talking about. Now, we've got sigma, which is the summation of pi, which is the proportion of class I, multiplied by log of proportion of, again, class I. Remember that the basis is, again, for the logarithm 2. This doesn't change, okay? From an information theory point of view that I'm not going to go into, the unit of entropy is bits. Yeah, the same bit that the whole computers are based on, okay? I'm not going to jump into that because I'm afraid that it might kind of not serve the purpose of this lecture. But remember that because the unit of entropy is bits, and a bit can either be 0 or 1, we always measure entropy in terms of the logarithm of base 2, okay? So it doesn't matter if you have 1 million classes or just 2 classes. The log has always the basis of 2 when you want to measure the entropy of a set. So don't forget that. Now, if we break this formula apart, now I'm going to just choose different values for I and kind of expand this formula a little bit. So if I is 1, we will get minus P1 log base 2 of P1. So since it's sigma, I'm going to have to sum it again. So this minus will keep repeating, right? So because this minus is being multiplied to every element inside the sigma. So I'm just going to kind of jump into that and just put the minus in the beginning of every term that I'm generating using the sigma. So if P is 2, it becomes P2 log the basis 2 of P2. And it will continue, right? So we'll go to P3, P4, P5 until we reach to the end, meaning that in this case we have C number of classes, right? 10, 20, whatever it is. So we'll keep going until we cover all the instances in our training set. Yes. Now, if you notice, so in the very end of this formula, we'll reach to PC log of PC. So, if you notice this first bit right here, the very first 2 expressions in this formula, isn't this exactly what we did to compute the entropy for a binary classification case? That is true, only we named P1 as P plus and we named P2 as P minus. So it's an identical case. So the binary classification case, my friends, is a special case of a multi-class classification case, okay? So these formulas are both the same. So I would recommend that you learn the more general version, which is this one that I just showed you, okay? It serves better for learning the decision trees. Now, in the case of binary classification, we told you that the minimum and maximum of entropy is 0 and 1, okay? But remember that if you have C number of classes, so C is a number more than 2, say 3, 4, 5, the number of classes that you'll have, in that case, the entropy as again the minimum of 0, but the maximum will always be log of C with basis 2. Okay? Then again, remember, this is a more general case, meaning that this also covers the case where we have C equal to 2. Let me prove to you. So if, let's say I don't want to even know about this rule over here for a binary classification. I just want to learn one formula because I just don't want to fill my head with different formulas. So in that case, since for a binary classification C is 2, I can see that the entropy of a set for a binary classification, on the left side I can see it's 0. And on the right side it is log of 2 on the basis of 2. And this, you know, that is equal to 1. There we go. So I would say we learn this general relationship. And then you can just replace C with the number of classes you have, and you can always figure out what is the maximum entropy and confusion that you can get in a particular subset. Right, let's wrap it up. So we said that entropy is a measure of confusion, and we said that the decision tree uses entropy to compute this magical number called information gain in order to decide which attribute to start the splitting from. Okay, so we didn't talk about information gain. That would be the topic of another day. But in the meantime, I hope that this has been informative for you. And if you want more details, please feel free to click on the link of the blog post in the description of this video. And you can also find the links to our Twitter, Facebook, and LinkedIn accounts of MLDone, so you can follow us and join us on those platforms as well. So I hope that this has been informative for you, and see you in the next lecture. Bye bye.